MacMillan Space Centre after our week off. My name is Michael. I'm the program coordinator here, if you don't know, but also with our astronomer, Rachel. Hey, Rachel, how's it going?
Oh, good. Good to be back.
How was your week off?
It was nice. I actually spent it, instead of being outside, I spent it reading a thesis that was over 100 pages. That is
Okay.
what I like to do in my fun time, apparently.
Well, tell us about what the thesis was.
It was cool. It was about using lasers to cool down atoms. And that was kind of related to my thesis where I looked at ultra cold neutrons, but this was looking at ultra cold atoms. So it's a little bit different, but still cool that you can make and cool down things with lasers.
So even in your time off, you're still working, still thinking about space, and
Always.
of course, the universe still runs even when we're on vacation. And there was some really exciting news that we'll touch on. You made a special video that we're going to release after this. We're going to focus on some big unanswered questions from the summertime. For this final presentation of the summer, but I think we need to talk about this black hole merger, the latest from the LIGO Observatory. So, what exactly happened here?
It's really exciting because it is supposed to be the largest black hole merger ever detected. And it was a merger between an 85 solar mass black hole and a 66 solar mass black hole. And they combined together to form a black hole around 142 solar masses, so pretty big. But the reason why it's interesting is because we have something called a black hole mass gap, where we don't expect any black holes to form from stars in this mass gap. And that's around like 65 to 130 solar masses. And the one that was detected, the 85 solar mass one, is right in the middle. And so that was kind of weird that we're seeing something in this range. And so scientists think that maybe that's because we don't have sensitive enough instruments that are detecting in this range. Or maybe there's something to do with our theory that we don't know. And so it was really interesting to detect an 85 randomly in the middle of this stellar graveyard solar mass black hole and from LIGO.
Interesting. So,
Yeah.
like I said, Rachel, you made a special video just dedicated to this, but we've got 30 minutes here for everyone out there on YouTube, maybe also watching on Telesoptic. Thanks for joining us. And we're going to get to all your questions. Rachel's going to go through all of the unanswered questions that we didn't get to from the summertime. And of course, we will get to all of your questions. So please put your questions into the chat. We will get to any and all of them. But let's start off with some of those big unanswered questions, Rachel, and
For sure.
with a little short presentation.
Sounds good. And as always, I'm going to share my screen. Hopefully you'll be able to see a panel that says curious questions.
There we go.
Awesome. Okay, so these are questions that I collected from viewers either by email or on our social media like Instagram and Facebook. And because the theme of this month is exoplanets, I thought we'd start off with an exoplanet question. So this is from Russ on Instagram. He asked, what about the newly discovered Proxima Centauri C? So Alpha Centauri is the closest star system and planetary system to our solar system. It's a triple star system that lies around 4.4 light years away. And one of these stars is called Alpha Centauri. And it also goes by the name Proxima Centauri. It has two known planets, one of them being Proxima Centauri B, which was discovered in 2016. And it was found using something called the radial velocity method. So the other planet, Proxima Centauri C, was first noticed in April 2019 in the radial velocity data from the European Space Agency's HARPS instrument. And HARPS stands for High Accuracy Radial Velocity Planet Searcher. Now, a year later, in April 2020, another paper was published with data trying to detect this candidate planet. And one of the images collected is shown here on the right. Now, if you take a look at this yellow circle, that's where researchers calculated the planet should be. But I don't know about you, but that little white dot in the center doesn't look all that different from all the other little white dots on this image. So the researchers weren't able to say for sure they detected the planet, even though they could calculate where it was going to be. Now, most recently in June of this year, the planet's existence was confirmed using old Hubble data from 1995. There was a Texan astronomer from the McDonald Observatory who combined several independent methods of studying exoplanets to confirm the presence of Proxima Centauri C. And I think that's especially cool because it shows how useful old data can be, because you can still get new information if you have new techniques to look at that data. Now, another question that I get very often is, what exactly does an astronomer do? Do I just sit here all day and talk about planets and space? In part, yes, but there's also other streams that you can go into in astronomy. And it really depends on where you fall. So a lot of people go into academia, and that's doing either teaching as a professor or doing research. And for that, you'll need a lot of school. You'll definitely need your master's. And if you're teaching, then a PhD is preferred and required for research. But then you get another third of people in astronomy going towards government institutions. So that's when you have people planning observational programs and data collection and analysis for things like NOAO or NASA or the CSA. And interesting enough, this is where the highest median salary lies, and that's with government institutions. And another one is business and private industry. So that's things like doing consulting for companies like SpaceX, Boeing, or Microsoft, or doing things like aerospace research for these companies. And the less than 10% includes myself, and that's science centers and planetariums, informal education, and public outreach. So there's a lot of things that you can do. I've also included a photo of Vera Rubin on the side because I think that's a very inspiring photo. But there's a lot of things that you can do in astronomy and astrophysics, and it all starts with having a passion in astronomy. Alrighty, and then now we're moving on to a question from Parker on Instagram. What are some exciting known unknowns? So we have a couple of open questions in astronomy. Two of my favorite ones to talk about are what is dark matter and something called the Hubble tension. So let's start with dark matter. What exactly is it? Well, dark matter is the stuff that makes it possible for galaxies and clusters to exist. When cosmologists calculated why the universe is structured or looks the way it is, it became clear that there simply wasn't enough ordinary matter, or what we call baryonic matter, to form such large-scale structures, things like galaxies and clusters. Now, the gravity of visible matter wasn't strong enough to attract and clump them into these structures or these filaments that you see on the cosmic webs. So what they would have expected is that stars would have been more likely to be scattered throughout the cosmos rather than bound in galaxies. So scientists figured out that there must be something else there, something else present, something that's dark or non-luminous that doesn't emit light or interact with electromagnetic radiation. And so we named that stuff dark matter. And the reason this is a conundrum is because we actually really know more about what dark matter is not than what it is, even though it makes up 95% of the matter in our universe. So my favorite joke is the joke that cosmologists only know 5% really of what they're talking about, because it's 5% ordinary matter and 95% dark matter. Now, so a lot of efforts around the world are trying to detect dark matter particles or make them themselves. And I've highlighted two efforts on the right-hand side. We have direct detection from LUX, where they're trying to detect dark matter particles. And LUX stands for the Large Underground Xenon Experiment. So they have these massive detectors, a lot of xenon buried underground, and they're hoping that maybe a dark matter particle will interact with the xenon, produce a flash of light, and they'll see that flash of light as evidence for dark matter. But they haven't seen anything yet. They're still holding out. But we have another effort, thankfully, and it's the indirect detection method from the Large Hadron Collider, or LHC. And if you take a look at the bottom two data images that are simulated of what we would see if we detected a dark matter particle, it's really interesting, because if you take a look on the left, this is with ordinary matter, but then on the right, you'll see that only part of this image or part of this detector has detected particles, and then there's a massive gap of nothing all the way around. And that's because dark matter doesn't interact with anything. So it'll fly right through the detector and won't be detected, and it won't show up in the data. So that's how they'll know they detected a dark matter particle or created one, by the absence of data, which I think is very cool. Now, another big question is something called the Hubble tension. This is a plot from the European Space Agency, and it shows the evolution of measurements of the rate of universal expansion, and that's the Hubble constant, over the past 2 decades. Now, everything was peachy up until the early 2000s, but now we've got genuine statistical disagreement. So we have different ways of measuring this Hubble parameter or Hubble constant, and they all give slightly different values, which is a big problem because this is our universal constant for the rate of expansion. So if we look at the cyan or blue color and the red color, these two observations are from UMAP and Planck respectively, and they're estimated from models fit to the temperature fluctuations that we see in the cosmic microwave background, which originated in the very early universe. So these two measurements are coming from the early part of our universe. And then we also have these measurements over here in this dark blue. And those come from measurements or observations of galaxies. And we all know that galaxies were born a lot later. So now we're looking at a different time period of our universe, and we get a different number. Now, on one hand, it's extraordinary that there's two such radically different ways of deriving this number, this parameter, one using our local mature universe and one using a distant infant universe. And it's interesting that these two numbers are super close to each other, but they're not quite in agreement. Now, that's what leads us to call this a tension, is because it's an oddity that still needs explaining. And in principle, these two numbers should agree. And if you take a look at this last little purple point over here, it's a single purple point, and that was obtained using coalescing neutron stars simultaneously in both electromagnetic radiation and gravitational waves. So there's only one point here, and that's because that was from only one detection of gravitational waves. And the discovery of gravitational waves was rather recent. In 2015, 2016 was the first detection. So we only have that one data point. So I'm hoping that with more and more detections from LIGO and Virgo, that maybe we'll be able to resolve this tension with the Hubble parameter. Now our next question is from Abby, and she asks, do stars sing? And this is a great question because you would think that there wouldn't be sound waves in space. Sound waves are longitudinal waves or compression waves, meaning that they need something to propagate through, a medium to propagate through. And space is really, really empty. So in theory, we really shouldn't be hearing any sort of sounds. But things like supernova, where you have a lot of material localized in one place and it explodes outwards and these pressure waves, then you might be able to have a little bit of sound. But the question is about stars. They sing in a different way than you might think. Now I'm realizing I don't think I shared my sound, so I'm going to stop sharing and hopefully share again. Is it back yet, Michael?
Not quite yet.
Okay. I can share a funny story. When I was trying to look up a video for stars singing, I came up with a lot of famous people singing random songs. So that teaches you a little. Yeah. So I had to refine my search a little bit.
Some Lady Gaga.
I think there was one by Justin Bieber and another by some other people that I don't know. But all right. So I'm going to play this video and it might be a little bit loud. So I'll warn you right now before I press play. And this is a video of singing stars. So you can't actually hear these sound waves in space. If I was to go into a spaceship and go by a star, I wouldn't hear them singing the lovely melodies of, let's say, Justin Bieber. But sound waves do propagate through stars all the time in many different waves. So sound waves sometimes travel only around the top layer of the star, like you see right over here, these little red arrows bouncing around the top of the star, or they travel deeper into the star, like these more triangular waves that you're seeing as well. Now, asteroseismology is a study in which tiny oscillations within a star can be used to probe its internal structure. And that's because the different oscillations are sensitive to different parts of the star. So astronomers can make inferences about the internal structure of the star, which wouldn't be possible from observing other properties from the outside, like brightness or surface temperature. It's really hard for us to probe the interior of a star. Now, the waves of a star, or the waves inside a star, can cause it to vibrate and brighten in ways that are really subtle that only the sharp vision of telescopes like the Kepler Space Telescope would be able to see. But by studying a star's interior structure, astronomers can learn more information about the star's size, composition, and age. Now, in these sorts of studies, astronomers can turn those tiny variations in a star's light into sounds in a process called sonification. And in the sonification process, frequencies of brightness variation are translated into audible frequencies that humans can hear. And that was the sound of these different stars that you've heard. Now, one use of asteroseismology is in searching for exoplanets, because these tiny variations in the star's light can also reveal planets transiting in front of their stars. So in short, stars kind of sing, but in a different frequency than us humans can hear. And one question from Abby is, how does this Hubble Space Telescope work? And that's really exciting because we do have the James Webb Space Telescope, which is following up as almost a replacement for Hubble. So it's interesting to see how Hubble works, and maybe we can extrapolate that to how the James Webb Space Telescope works. So the Hubble Space Telescope is not the kind of telescope that you look through with your eye here on Earth. Hubble actually uses a digital camera, so it takes pictures much like a cell phone. And then Hubble uses radio waves to send those pictures through air back to Earth. Now, a common misconception is that a telescope's power lies in its ability to magnify objects. But actually, it comes from the fact that telescopes can collect way more light, or way more photons, than the human eye can. The larger a telescope's mirror, the more light it can collect. You can kind of think of it like photons coming from a distant star, and we have a telescope lens that's kind of like a rain catcher, the photons being droplets of rain. The bigger you have your rain catcher, the more photons you can collect, the more rain droplets you can collect. Now, more specifically, the Hubble is a Cassegrain reflector telescope. And that just means that light enters through an opening, it bounces off the primary mirror onto a secondary mirror, and then the secondary mirror reflects that light through a hole in the primary mirror onto a focal point. And so the path of the incoming light looks kind of like a W, but with 3 downward hubs instead of 2. Now, a follow-up question is, well, why didn't we just have Hubble here on Earth? Why did we send Hubble up into space? Well, we sent Hubble into space, and we're sending other telescopes into space because we have an atmosphere. And that's something, a problem that telescopes have faced since the earliest days of their invention. So we have 2 main problems when it comes to our atmosphere. We have shifting air pockets, or fluctuations in the atmosphere, that distort the view of telescopes on the ground. But the same atmospheric distortion is actually the reason why stars twinkle. So it's kind of nice to have it for twinkling stars, but not so nice for trying to view distant objects with our telescopes. Now, the second is that the atmosphere actually partially blocks or absorbs certain wavelengths of radiation, things like ultraviolet, gamma rays, and X-rays, and they get absorbed in the atmosphere before they can reach Earth. But researchers can best examine an object like a star by studying it in all types of wavelengths that it emits. So we want to have some telescopes on the ground and some telescopes in the air that can capture these wavelengths that would otherwise be absorbed by our atmosphere. Now, newer ground-based telescopes are using technological advances to try to correct for that atmospheric distortion, things like adaptive optics. But there's no way to see wavelengths that the atmosphere prevents from reaching the planet. So the most effective way to avoid these problems of the atmosphere is to place your telescope beyond it. Or in Hubble's case, we placed it 569 kilometers above the surface of the Earth. All right, and that brings us to the end of some curious questions that I picked out from this summer.
Awesome. Yeah, we've got lots of questions, but if we just go back to some of the ones that you did have, I know that you did talk about what an astronomer does, which is actually a question that we get a lot here.
Yeah.
I remember I got that question before we even had an astronomer here, and I answered that question. It was long and rambling. I remember the child that asked the question wrote down in the notebook, because they were interviewing me, and they just wrote down "look at stars," which I thought was kind of cute, because I think that is actually the actual definition of an astronomer, is someone that looks at stars. But that means for all astronomers, right? Because we can all look at stars and be curious. And speaking of being curious, we do have some questions. So Mara, who's watching from Surrey, wants to know the best way to look at the nighttime sky. So Samara, as she told us, is 7 years old, wants to look at the stars. What's the best way to start?
Well, I love your passion and enthusiasm. The best way is to go to somewhere with the lowest amount of light. So we talked a little bit about light pollution a couple of weeks back, And so you want to go to the darkest place possible. There are some places that are designated dark sky locations that don't have anything like street lamps around that will cloud your vision. And you also want to go at night and also dress warmly. And you also want to let your eyes adjust. So that means no looking at your phones, no looking at your tablets while you're viewing or before you're viewing. And you want at least 30 minutes to let your eyes settle and dark adapt to your surroundings.
Awesome. And just to let everyone know, we will be actually focusing all on what's up in the nighttime sky with our next live Q&A with Rachel. But we are going to be switching up a bit of the pattern as we head into our fall school season. So we're going to be here with our Q&As with Rachel every 2 weeks. So don't tune in next Thursday, but in 2 weeks we'll be back, and the theme will be all about what's up in the nighttime sky as our evenings are getting a little bit longer. We're going to have more opportunity to look up at those stars. And also this month, we're going to be doing themed months. And also continuing months. This theme is exoplanets, which was the first question you got about exoplanets. And we're going to be having a full cosmic night on which is our evening program. Michelle Kunimoto from UBC, who has discovered some exoplanets, is going to be with us. So make sure to check our website, get some tickets for that event. That's going to be exclusive in Zoom. Really cool event all on exoplanets. And then next month, we're going to be doing dark matter. Which relates to another one of your questions. So all of the big questions in the universe, we are going to be tackling next month. Make sure to check out for that. One of the questions Pride wanted to ask, and I think it was related to when you were talking about dark matter, which was you were talking about supersymmetry, or at least like her question was, are you talking about supersymmetry? So maybe first, maybe define what supersymmetry is, and then maybe see if that relates to what you were talking about.
So supersymmetry, or SUSY, because it's SUSY for supersymmetry, is this idea that all the particles that we have on the standard model have a counterpart, and they have a supersymmetric particle. And these supersymmetric particles are extremely heavy. And so what I was talking about with the Large Hadron Collider is not quite looking for supersymmetric particles. It's more so using actually one of Newton's laws. So having this idea of every action has an equal and opposite reaction, and same thing with conservation of momentum, and that if you have a particle going off in one direction and a dark matter particle going on another direction, we won't see the corresponding data or the momentum data on the other side of the dark matter particle because it's not interacting with anything, and so we'll see a gap in that data. And the interesting thing about supersymmetry is that it's almost a little bit of a dying concept because we haven't found a lot of supporting material for it. But it was one of the explanations for the mass of the Higgs boson, or prediction for the mass of the Higgs boson. And so they had two leading theories. One of them was supersymmetry. And when they took a measurement of the mass of the Higgs boson, it ended up being right in the middle of their two predictions. So that was kind of funny that it was a happy day for particle physicists, because that means that their research field can continue and there's still more questions to be had. But it was kind of funny that neither of their predictions worked out.
Once again, this happens like another prediction, because this happened with the black holes as well. Something happening right in the middle. Now, what do you think that? Where do you think that that's coming from? Like as a scientist, let's put you in one of these scientists' shoes. When you get this data and it comes right in the middle, what is that? Does that worry you? Does it, like you said, it is kind of exciting, but does it tell you that your methods are on the right track?
That's an interesting question, and I'm going to answer it by the way that physicists think, and that is tackling the extremes first and then kind of filling in the middle details later.
Yeah.
So things with black holes, we're looking at the lighter end of black holes and the heavier end of neutron stars, but that in-between transition period, or where that mass gap is a little harder for us to fill in, especially starting from theory, because theory starts from these extreme conditions. We take things like what happens if you take time to infinity, or give something zero mass or zero drag. So we try to make things as idealized as possible, and then reality kind of messes with that a little bit, and that's why we have that kind of in between blurry areas.
Yeah. Okay, interesting. Well, and yeah, and as a scientist and as somebody that looks at the universe, this is your way of understanding it. But then, of course, in this theme is unanswered questions and curious questions. So, in our last few minutes, let's just ponder about some of those unanswered questions that maybe science can't answer. And the only way that you could would be to speculate. And I know speculation is not something that scientists like to do, but we'll allow you to speculate here, Rachel. And is there something out there, an unanswered question in the universe that we don't have an answer to, but that we can only speculate? What would you choose?
Ooh, probably the idea of multiverses. I get the question a lot, especially from little kids asking if we are the only universe to exist. And the answer to that is almost kind of a non-answer, because we have an observable universe that is within a larger universe. And our observable universe contains all the stuff that we can actually see and would be able to interact with. And that is the distance that light has traveled since the beginning of our universe. And that happens to be this boundary of things that we can see and interact with. And what's beyond that, we can't ever know, because we can't look past that. So this idea of multiverse theory, or other universes existing outside or beyond that observable universe boundary, I think is kind of a non-answer, because we can't ever detect anything that's past there. So there's ideas like bubble theory, where our universe, or our observable universe, is a little bubble, and that there's other bubbles out there that contain their own universe, they contain their own laws of nature, physical constants. I like to joke that maybe there's a universe where pi is 3 and all our lives are a lot better in math. But yeah, that's one of the main questions that it would be very, very difficult, if impossible, for us to be able to answer.
Right. Yeah, no, the multiverse theory is super fascinating. And then once you sort of like get onto that path, and again, that gets into theoretical physics, which of course is sometimes a bit, sometimes in, excuse me, conflict, with physicists, because physicists, and astronomers, they work in the real observable universe. And I always like hearing their arguments and their debates. It's always really fascinating. One final question, of course, we're going to go back to Samara. She asked our first question, which again is another common question, Rachel, because we talked about what do astronomers do. Well, Rachel, have you ever been in space?
I wish I could say yes. I really do. I haven't been in space yet, but I am floating in my Zoom background above Earth. If I could be sent into space, I would absolutely do it, because of the idea of the overview effect and being able to see the world as this blue marble, and not seeing any borders, any boundaries, but just one planet and one Earth with everyone on it.
Right. And would you go?
For sure. Yeah. If anyone knows or has any contacts with the CSA, just pass along my email. That'd be great.
Awesome. Well, thank you so much to everyone that has joined us for another session of live Q&A with Rachel. And like I said, we're going to be changing up our schedule a bit as we head into the new school year. And the best way to keep on tabs with that is to like and subscribe to this YouTube channel. We are going to be really focusing in on a lot of the content that we're putting on here. So liking and subscribing, sharing with your friends really helps us out. And as we go into the school year, we're going to be focusing on school. So if you are parents out there that are sending your school into school, or maybe you're keep your kids at home and homeschooling them, we are going to be doing programming dedicated to you. So make sure to check our website to see what programs that we have available, or send your teachers onto the school listings that we have there as well. And of course, if you would like to just donate to us, so we can keep doing the work that we do, you can go to our Donate Now button that's on our website. Like I said, we'll be back in 2 weeks to tell you all about what's up in the nighttime sky, how to find it, and then we'll also be here in 3 weeks with our Cosmic Night evening program, all on exoplanets. So Rachel, I will see you again soon. Everyone out there on YouTube land and Telesoptic, see you next time.